So our second section today in our first lecture is called The World of Chip Design. And I wanted to start out by discussing a little bit of what we have inside a computer. Okay, so we all have a computer. It could be a desktop, a laptop, could be a tablet, and all kinds of other things. So we usually would have this type of a box with, a traditional computer would have its monitor on top. I don't know if many of you guys have seen this type of thing, but that's how my computer started out. It had like a floppy disk drive, and maybe at some point there was a hard drive inside. Anyway, this was our computer, but basically inside the computer there is this big board underneath. And if we take this board, which is called a printed circuit board, a PCB, it's this big green thing, it has all kinds of different things on it. So first and foremost, inside usually we'd have this chip, this big chip called the microprocessor, or the CPU. And this chip was a chip that could do anything. It was a Turing complete chip, so we could program it to do all kinds of different things. And there were all kinds of peripherals. For example, we may have had another chip that was a memory. It could have been an SRAM or a DRAM, or that's a memory chip. And these are connected together with all kinds of wires that connect them. Okay, and then we have all kinds of other things like that hard disk we had. Okay, and it's also connected by all kinds of wires to different parts. We of course may have some sort of a battery, depending on if this is a mobile or not mobile, and what the different batteries and things do, and they give power to the different parts. Okay, and we probably have some sort of a clock, right? A clock that gives us a clock to all this, and all kinds of other different things that are around here. We may have a graphics card or something that's connected to the screen, and we have all these different things that are connected to each other. Well, on this printed circuit board, first of all, each of these things has to be connected to it, and they have to have these wires that connect to each other and so forth. And these wires are long, they're big, we have to print them, so they can be centimeters long, they can be millimeters long. And also, if we want something mobile, such as a phone or something like that, we want to have everything be integrated integrated one with the other on a very small form factor, especially if we want things that are extra small, such as a pill that we're going to swallow or different things like that. We want to have all of this be as small as possible. Due to the fact that the wires are long, and due to the fact that we want things small, and due to the fact that just we have to take each one of these components separately and assemble them together, what has happened in the last many years, in the last few decades, is basically we've been able to integrate more and more components or systems, components onto a single chip. And so we've been able to drive a lot of the different chips that we used to have on different systems onto one chip. And so therefore we call it a system on chip, or SoC in short. Okay, so nowadays, as much as possible, we put on a single chip, and we call it a system on chip. There will be actually several systems on chips in a lot of systems that will be connected together, but we try to put as much as possible on this chip. So let's dive down into what we have in this chip. And again, if we learned a previous digital circuits course, we learned how to make like a CMOS inverter. We saw it was a couple of transistors that were connected together in such a way. And we saw that the size of this inverter, maybe if we're talking about like nanometer scale transistor lengths, so these things will be around a micron or so, a few microns squared. They're really small, okay? And there'll be lots of these, and they have to be connected together. And there may be all kinds of analog blocks too. We learned maybe in an analog course about some sort of an analog amplifier or different parts like that. And they're really small, and they or we try to make them as small as possible. They may be big, but they're not this centimeters or millimeters scale. They're in the micrometers or even the nanometer scale. And as we started to kind of discuss, there might be millions or billions of these scattered around the chip. And they're really, really, really small. So when we take our chip, we have this area that we usually call the core area, where all of our logic, is scattered around. So that's going to be a whole bunch of these, and I'm talking about a lot of these transistors that make up these gates, and some of these analog blocks, and a lot of memories. Usually we'll see the memories as a bigger kind of a block, like in all kinds of places around the chip. Okay, but everything else is going to be these different gates and transistors, and maybe again here's some sort of analog block, maybe like a PLL or an ADC, or different types of blocks like that will be around. Okay, so we get this chip, and we'll discuss it a bit more in a second. But what we need to do is then we have out here, I don't know, we have, say, the battery that gives the chip its voltage, and we have the clock that we saw, and those are outside the chip. They're on a different chip or whatever, and we need to drive them into the chip. Well, here we have this. On the board we have this big wire, and it's many orders of magnitude larger than this. So what we need to do basically is we need to have an interface between this wire and this chip, and that is done through something that we call the package. So there's going to be on top of this some sort of a mechanical structure called a package, and the package will have these connections on it that we can connect this big wire to. So they're big enough for a machine to actually connect it, and possibly inside the package there's going to be some more type of wiring that's going to go into into something that can interface with the chip. But the interface to the chip is not going to be nanometers. It has to be much bigger, maybe like 100 micrometers, and we call this thing a pad. It's going to be part of the chip, this pad, but it's big enough that we can take a very small wire and actually connect it to it with a machine, with an external machine. Okay, and we have to have that pad interface with the rest of the chip. And for example, if we want to drive a signal from the chip outside, what we need is some sort of a buffer, some sort of an inverter, a thing like this, but not a small one that fills up this little tiny capacitor, but rather something that is able to fill up these huge capacitors that are many orders of magnitude larger. So what we're going to do is we're going to put this buffer or inverter or something like that that's really big. It's many thousands of these little transistors and gates that are that are connected in parallel, and we're gonna make a little block like that that's going to be on the chip, and we're going to call this an I/O. Okay, an input-output block. And what we're going to do basically is we're going to take these I/Os, and traditionally we're going to put them all around the chip. Okay, so each of these guys, these really huge guys, because they're the size of maybe thousands or even more than that, digital gates, these are called I/Os, and they're going to be connected to these pads, which are something that can then be connected to the package, which can then be connected to the board and connect to our other chips and our other things that are outside the chip. Okay, so that's kind of what we have. Again, our chip in my picture over here, it's actually, this is the edge of the VLSI, the edge of the chip. This part over here already is the packaging, which we may learn about in a future lecture. So I just want to say one more thing, that okay, we have this battery now here, and the battery is connected to the chip in some way, again through these pads. We're going to drive these voltages into the chip, and there's going to be the voltages are going to get into the chip. How do we bring this voltage over here so we have a VDD and a ground on this guy? So what we're usually going to have is we're going to have all kinds of wires inside the chip that are going to be able to move this VDD and ground over to the gates. Usually that's going to be in a way that we're going to build these rows along the chip, where each of these rows is biased at a voltage, say VDD, ground, VDD, ground, and then we're going to build our gates themselves to be like little Lego blocks. They're going to be a certain size that can just fit exactly into one of these rows. Okay, so inside here is an inverter, and it gets its VDD from here and its ground from here, and we'll put another one underneath, and there it's going to get its ground from here and its VDD from here, and this may be a NAND gate, and they're all going to be exactly the same height so they can fit into these rows. Okay, and what we're going to have is we're going to have some sort of grid of power on different types of levels. So this is going to be another type of a bunch of things. This may be VDD, and this may be ground, and then we're going to have a connection. So this VDD connects to the green VDD, and this ground connects to the green ground, and so forth. So we're able to take whatever this wire is, and as long as it's touching in one, or it's usually going to be touching in many more places, we're going to be able to dissipate the power all over this chip. So that's kind of just a few basic things I wanted to discuss about what we have in an integrated circuit chip. So just an example of one of these types of chips that can be made, and this is an example that we've recently fabricated and is now being measured in our labs. We call it SoC2, System on Chip 2, because it's the second big system on chip that we made in EnICS Labs. We've made many chips, but this is the second big, huge national project. Our internal name is Negev, which is a desert area in the south of Israel, and that was the internal name we decided to call it. So with the chip, what we do usually is we build an architecture, and this is the basic architectural block diagram of the chip. And you can see, if you look inside, that we have these X2 blocks. These are DSP cores, or they're a type of a CPU core. So there are 4 of these kind of microprocessors that we have on the chip. Each one of them has a separate data and instruction memory, or what we call a level 1 cache. So each one of these has that type of a thing, and each cluster of 2 has this level 2 type of a cache. And then we have in different places all kinds of other things. So if we look, we have these slow peripherals over here, which are things that talk to the outside world, such as I2C and UART. And then we have some fast peripherals, such as an Ethernet, thing. And then we have some sort of L3 memory over here on a special technology that was developed in my lab. And we have a test port and all kinds of other things. These are all connected together by some sort of interconnect, a network on chip over here. And this is a basic type of a block diagram that you may have when you start to build a chip. Well, let's see how I erase all ink on slide. Okay, this was then laid out in different CAD tools that we'll learn in future lectures. And you see that we have this physical structure, which has around the sides, you have these IOs that I was discussing. And they're pretty big relative to transistors, because there may be many millions of transistors inside the chip, and there are only a few hundred or even less of these IOs. These little round things are called bumps. That's how we connected the package, and these are different blocks. So what we actually see here is that those four cores are these guys, these X2s. These are the 4 cores which have their memories inside them, their level 1 caches. And here are their level 2 caches outside somewhere. And we have, this is all a bunch of memory that's our level 3 cache. Okay. Besides that, we have some innovative parts in this design, and these include a couple of things which I didn't show before. These are all these blocks that are called embedded FPGAs. We'll discuss later on what FPGAs are. So these are FPGAs that are on the chip that we can program the hardware inside them. And then we have this block here is some of embedded memory that my research group developed. We have here some special logic that was integrated into the ALU of this core that was built by Professor Alexander Fish's research group. And we have some very special temperature sensors that were made by Professor Joseph Shore's research group. So we did all this in a research environment, and we integrated our research into these things. Okay. Finally, we taped out the chip. We sent it to a fabrication plant that made our chip. We put it in this package. You see, this is a very special type of a package, and it was integrated onto one of these boards. This is a test board. The board probably wouldn't be this big if we were selling the chip, but this is completely a test chip for testing these different structures we have on it, and it has all kinds of ways to connect it to machinery. And then what I'm gonna show you here is just a short demonstration of what the chip can do. So this is the chip in the lab. You see here the PCB. with the chip on top of it, and it's connected to an external computer that in a second we'll see. It's running an application that we can talk to the chip through some sort of a scripting language. So we have some C code that we wrote to boot the chip and to see if we can get it to work. And over here, we're going to turn it on, and we're going to see that it actually, we have a scope that's checking, and this is telling us that the chip was able to boot, and that it's alive. And this was on the first day of testing, so we were very happy when we actually measured this thing. And then our terminal is telling us, is replying to us with all kinds of signals. It's telling us that it's alive and it's working and everything is good. So that's the type of thing that happens when you build a chip. You take it from this design that's written on a piece of paper until you get to the lab and you see that it's working. It's a long process. It can take a couple of years, in fact, to do all that. But once it happens, it's very exciting. So how does this happen? We need an ecosystem, a very big ecosystem, in fact, for this to work. So this ecosystem starts with what we call the fab or the foundry. Fab is short for fabrication plant. So it costs a real lot to make these chips. In the past, it wasn't as expensive, but as the technology has gone and scaled and become really complex, it can cost many billions of dollars to actually build one of these types of plants. For example, Taiwan Semiconductors, TSMC, which is the biggest fab or foundry in the world, they just announced a couple of months ago that they're building a 3 nanometer fab. And it's going to cost, I can't remember, but something around $10 billion to make. That's a lot of money. Only a handful of companies can actually make such a fabrication plant and can maintain it. It costs a fortune to maintain it as well. So there are only maybe 10 or a few more than that, but real companies in the world that are actually producing the chips, and they're called foundries, which means that they actually provide the technology to the rest of the world. They're like a printing house. So they, when you are an author, you don't actually go out and print the book on your home printer. What you do is you send it to a printing house, and they make many copies for a low price, but it costs a fortune to make one of these printing houses. So all these guys, TSMC, Tower Jazz, is an Israeli fab. Global Foundries is one of the big fabs. They all are these foundries, or they have their fabrication plants. Now, some of them, such as Intel, they actually have both the design. They do the design, which is this side over here. So you can see that Intel is on this too, and they make their own chips in-house, but that's very uncommon nowadays. In the past, that was the only model that existed. On the other hand, most companies are what we call fabless. So these are chip design companies. They make chips, but they design them completely on a computer and just send a file over to the fabs to fabricate them, and then the fab will send back the chips for testing at the companies themselves and for selling them at the companies themselves. So we have huge companies such as Qualcomm, and Samsung actually is over here too. I didn't write them on this side, but now Samsung is actually the second biggest foundry in the world. NVIDIA, Israel's biggest chip design company, Mellanox, was recently purchased by NVIDIA. And of course, this big piece of fruit over here, these are all companies that you may not think of them as traditional chip design companies. Some of them, yes, but like Apple is a systems company. They sell our iPhones and maybe software and so forth, but they also are producing their own chips. Another big player in the field that recently joined is Amazon. So Amazon has a big chip design center here in Israel, and they're producing chips. So all of these companies, they don't actually fabricate the chips. They don't have the machinery to make the chips. What they do is they just design them on a computer and then send them to the fab, which actually makes the chip. In the middle, we have another important player, which is the CAD or EDA. CAD is computer-aided design, and EDA is electronic design automation. Electronic design automation. Usually, our field holds the name EDA. CAD is a generic name that is used by many other fields other than the VLSI. So these are the guys who provide the tools that communicate basically between these fabless and the foundry. So the foundry is able to make transistors. They characterize the technology, and then they make some sort of file that tells what the technology does, and they want to provide it to the chip design company so they can design with it. Well, these different companies, Cadence, Synopsys, and Mentor Graphics, have a basic monopoly on this CAD area. They provide tools that can read these files that are produced by these guys and provide some sort of interface that these guys can design with them. So then over here, the fabless companies, they design whatever their chip is supposed to do, and then they send the files over to the foundry, and the foundry can produce them. So the CAD EDA vendors are very important in this field too. This is all done commonly in what we call CMOS technology. So hopefully in a previous course you already saw that CMOS technology is this thing over here. CMOS is complementary metal oxide semiconductors. So a metal oxide semiconductor means that we have some sort of a gate, a gate access port. We have some sort of a oxide that separates the gate from the substrate, and in the substrate we have the channel over here, which is separated by two diffusions, two areas or active areas that can talk to each other. In CMOS technology, complementary MOS, we usually have this substrate which is p-type, and we put in these n-type implantations into them, which creates an NMOS transistor. If we put something called an N-well, we make the substrate become N-type, and then we put P-type diffusions and we make a PMOS transistor. So in a technology where we can make a PMOS and NMOS within the same wafer, the same circuit, we call that CMOS, complementary MOS. And this is kind of what it looks like. So we need to be able to make all these types of parts. And this part where we make the transistors, what we call it front end. FEOL, front end of the line. That's where the logic happens. That's the transistors. That's what's making our things work. And so we use this name front end for many different things. For example, when we design with a hardware description language such as Verilog, we usually call it front end design because that's where the logic is happening. And that's basically these bottom layers. They're the most complex layers. They take a long time to fabricate and so forth. But in order to connect them, so for example, this blue stuff over here, what we do is we usually stack many layers of metal interconnect on top, which are connected by these like tunnel type things. So we have these metal interconnect layers that are connected by these tunnels that go between them. And these are commonly kind of a more simple process than making the transistors, even though nowadays, as we'll learn, it's also a pretty complex process. And we repeat it as many times basically as we want to make higher and higher interconnect. That's similar to building a building where we have a piece of land that is if this is our map and we have a little piece of land on top of it and we want to put as many whatever apartments or office space inside this little piece of land, which costs a lot, what we're going to do is we're going to build a big building on top so we can have many different offices or apartments on that same little piece of land. So the same thing we're doing here, we're building to in a third dimension in order to use this really expensive real estate and connect as many things as possible. So this is an electronic microscope picture of what's happening inside, and you see this kind of structure where we have many of these layers on top of each other. The building these layers of interconnect of these wires, we usually call it BEOL, back end of the line. So this is back end of the line. And usually a guy who does Verilog and verification and stuff is called a front-end engineer, and the ones who actually make the connections and put the transistors in place, they're called a back-end engineer. And that leads me to what we call VLSI Design Styles. So due to time and cost constraints, very few teams or companies develop products from the device level through to the system level. We usually use various design styles to shorten the time to market and development costs. We have to take into consideration trade-offs as always, and as abstractions are designed generically and therefore come with some overhead. So we're going to discuss 4 types of design styles: full custom design, standard cell ASIC design, field programmable gate array FPGA design, and we're just going to touch on microprocessor or software-based design, which is not the focus of this course at all. Okay, so the traditional style is what we call full custom design. That's how it all started. And over here on the right, we have a picture of the Intel 4004. This was the first microprocessor, the chip that made Intel, the probably leading company in chip design for the last 30 or something, 40 years. As you can kind of see, each of these lines was drawn by hand. In fact, from what I understand, this picture was hung up in the Museum of Modern Art in New York because it's really a work of art how they made this. There were only 2,300 transistors here. They could take 2,300 transistors and decide how they were going to actually put each one and connect each one, and it took a long time to do, but it was doable. Nowadays, we're talking about many more than that. Well, it's not 2,300,000, it's more like 2,300,000,000 transistors, or even more than that. And we need to put those transistors, and we cannot actually go and define them by hand. So we have moved on from this full custom design style where we cannot actually do this thing where we draw each thing by hand. If we could, then we could probably get the best performance for each and every little piece of the circuit, or we could get something that's optimized to fit the best way. But since it's impossible to do it, what we do is we rarely ever use it. It costs too much. The time to market is too high. However, in analog design, this is often used. And of course, when we make our lowest blocks, like for instance, designing one single inverter, we'll do it with this full custom type design. That leads us to what is kind of a semi-custom style, which we call ASIC design, application-specific integrated circuit, or standard cell design. So as I discussed before, we have these rows along our chip, and we make our standard cells. So each cell, each type of gate, is a certain height and a certain width. A certain height basically, and it's covered on the top. There's a line of VDD, and on the bottom there's a line of ground, and then we somehow put our transistors inside, which we'll discuss, so they can connect to this VDD and ground and fit straight into one of these little rows here and just snap into it. So that's kind of standard cell design. It's not we can't get to as high as optimization as in full custom design, but still this gives us the freedom of putting each gate wherever we want to put it almost, and being able to use whichever gates we want, which is really good. But it also is very expensive, and once we design this thing and fabricate it, well, if we put an inverter here, that inverter is going to be there, and if it's connected to this inverter, it's going to be connected, and we can't change it after fabrication. But we will, this is the main thing that we're going to be discussing in this course, and if you watch my other course, my digital VLSI design, they're discussing standard cell and ASIC design. This is the main way that we're going to be doing things today. When we have high volume chips, this is the way that they're basically made. But we have a third style, which is very, very popular, which is called field programmable gate arrays, or FPGA. As I said before, the biggest problem with standard cell design is that once we make it, once we fabricate it, we cannot change it, and it costs a lot. It costs millions of dollars to make one chip, so it's really a problem if we have some sort of bug or any type of problem with that chip. And therefore, there's something that was made called gate arrays, and changed eventually into field programmable gate arrays, where we actually take generic cells, and these are maybe called LUTs, lookup tables. See, LUT, lookup table. They're a generic cell which can take a number of inputs, and we program this lookup table to make some sort of output, so we get some sort of Boolean function. F of A, B, C, D in this case can equal something, whatever we want to program it to. Then we can decide if we want this is a flip-flop. We can decide if we want to sample it or not, and we can use this type of a cell as any type of a generic cell. It also gets its clock and so forth. Okay, we prefabricate lots and lots of these lookup table cells. Okay. Lots of them, as many as possible on a chip. And then we have these types of routers where we can decide each type of cell where the output connects to. And in this way, if we provide some sort of an EDA tool, which the companies that make these do provide, we can actually design any type of hardware we want. And this is very popular, especially now because you can put so many transistors on a chip that you can make many of these lookup tables, and you can do very, very complex things on these chips. The very good thing is that we can do this almost immediately. I mean, we go out, we buy one of these FPGAs from companies like Xilinx or Altera, which is now owned by Intel, and we can go and design our RTL, our register transfer level, which is like a Verilog type of a description. We just synthesize it and map it onto one of these things, and we can run it right away. That can be done immediately, and it costs very little. We don't have to go through this tape out and this hard, what I said, ASIC design. However, the problem is that each of these chips costs quite a bit of money. So if we need to be selling millions of these, our minimum cost per chip is whatever it costs us to buy one of these guys. And so it's not the best thing for a big mass production. And the other thing is, since these are not optimized, we again pre-place all of these lookup tables, and we use these complex routings to connect between them. We leave a lot of performance, power, and area, of course, on the table. Okay, so when we discussed the design style pros and cons, we saw that full custom design is very customizable. We can do whatever we want and optimize it for power, performance, and area, but it's really, really complex. The cost, the time to market are very bad, as is the risk. We may have made a bug, and if we tape out with that bug, our chip isn't going to work or isn't going to work well. Standard cell design is a much more simple, fast, and reliable way of doing this, because we have very robust methodologies for carrying it out. It still is time consuming and expensive, but much less than full custom design. It only works for digital design. Okay, we can't do this with analog design, and we are not as optimized for power, performance, area as possibly we could get for full custom design. And finally, we have FPGA, which, first of all, it allows us post-silicon configurability. So after the thing is fabricated, in fact, we buy the chip that's already fabricated. We can configure it and program whatever we want, and therefore, making one is very inexpensive. But when we have a high cost per chip, so if we want to make millions of these, it's very costly. And the other thing is, it's very non-optimized for these power, performance, and area. However, it's much more optimized than the other way that any software person knows, which is using a microcontroller, which means we write a piece of program in a high-level language, and we compile it and run our software instruction after instruction on the thing. It's programmable. It's very inexpensive. We all have a computer at home. We can do this immediately, but it's much, much slower and less optimized than using any of our hardware things that we have up here. We are not going to be discussing this in this course. And that leads me to another fun part of our course, which is called the Computer Hall of Fame. So IEEE put out something called the Chip Hall of Fame a few years ago, and in my other course in Digital VLSI Design, I provide one of the members of the Chip Hall of Fame during every lecture. Here I decided to make kind of my own Computer Hall of Fame and choose different computers that I will highlight every lecture. So I will start with the first computer, with the parents of all the computers, and with the father of computing, Mr. Charles Babbage. Mr. Charles Babbage was a genius in the 1800s who thought about how to make computers before they had things like electricity. These were steam-based, and they were completely mechanical. And he designed two computers, the difference engine and the analytical engine. The difference engine was his first project that was built to solve polynomials. The government of England put in 17,000 pounds, which was a real lot of money then, and then got fed up with the project and said it was too expensive and made him leave it. So the difference engine never came to fruition. And then he started working on the analytical engine, which was a much more complex type of a machine. These machines, they were amazing because they featured things such as ALUs, basic flow control, punch cards. The analytical engine was actually the first time where he said to use some sort of a storage system, like to show the instructions. Punch cards were the way that you'd have like a disk drive back in the day. To use these punch cards as how you bring your program into the computer. That was part of the analytical engine, some integrated memory. Neither of these were actually fully built. The difference engine was taken later on in the 1980s and built, and in 1991, a working example was shown at the Museum of Science in London, and it actually works. It can run So his design, which was on paper and never fully built, it actually works. The analytical engine is actually a kind of a compilation of several different machines, and it never, the whole thing was never built. Different parts of it were built in the early 1900s, and other parts were built since then. There's even a project to build a full working analytical engine today. So that's just a bit about Charles Babbage and the first computer. So with that, we discussed the world of chip design, and in the next lecture, we'll discuss how a chip is born.